Binomial distribution is the main discrete distribution that we'll be studying, other than the tables that we had. When we're looking at the binomial distribution, it's going to include a very complicated formula that I'm going to try and break down for you in easier terms, but it is going to require us to use a calculator, and specifically this unit, this section is going to require a button on the calculator that some calculators may not have. So in the original syllabus, I suggested that you either have a TI-30, which has the button I need, or a TI-84, which is a little beyond what the class needs, but would have the button. The TI-30 really should cost between $10 and $15. It should be reasonable either if you get it online or through Staples or something like that, but basically you will need to find something that has that button in order to use this formula. So the binomial distribution, we're going to look for what situations fit it, we're going to apply the formula, and we're going to solve word problems using the binomial distribution. It's a lot of words, I apologize, but really the goal here is to help you find the button on your calculator. So in order to successfully utilize the binomial formula, you need to find the combinations button. Most calculators have them, but generally they're not available on a basic phone calculator. Ideally, you'd have access to a TI-30 type calculator while doing these problems, or a TI-84. So I'm going to show you. This is my TI-84. I have this because I teach calculus and you absolutely need one of these for calculus. If you were going to go on and do Algebra 2, Pre-Calculus, Calculus, you probably want one of these. If you were going to go on and do Stat 2, I'm probably going to use this in Stat 2. So I understand that these cost like $100, $120. It's not a reasonable thing to buy if this class is probably your last math class you're going to take. That said, this is the one that I have around that I'm going to show. I'm going to do my best to talk you through how it would be on a TI-30 as well, or any other calculator you have that could possibly have this button. So on a TI-30, there's a button marked PRB for probability. So it's in the top left-ish of the calculator. When you press this PRB button, there's three things that come up. The three things that come up are exclamation point, NCR, and NPR. For our formula, we want to use the NCR button. NCR means combination. It's a formula in itself where it's taking a factorial divided by another factorial and doing a bunch of complicated stuff that I don't want to get into. That said, what it's going to look like on your calculator is you're going to put in a number, then press the NCR button, then put in another number. So if I wanted to do 4 NCR2, in some calculators it shows lowercase n, capital C, lowercase r. On other calculators it just shows it as a capital C. So if I were to enter 4C2 into my calculator, I'd press the 4 button, go to the probability menu to get NCR, then press the 2 button. On the calculator screen it would read as 4 NCR2, and when I pressed enter the answer should be 6. I'm not going to get into why the answer is 6, but basically if you are putting this in correctly and getting 6, it's telling you that you've identified the right button on your calculator and that you're able to put it in correctly. On a graphing calculator like mine, it's a little more complicated where to find it. In order to find it, I would first have to press this math button on the far side, which is below alpha. After I press this math button, I'd want to move to the right using my cursor over to the far right column marked PRB. Once I'm in that column marked PRB, the third option is NCR. Again, in order to put this in the calculator, I'd want to first put the number that's in front, like 4. Then I'd press the math button, scroll over to the far right column PRB, and select the option NCR. After pressing enter, it would show up on my calculator line, and I'd put the 2 after it to say that I want to do 4 NCR2. When I press enter, it would then tell me the correct answer of 6. So that was just a quick, here's the calculator button we're going to need in a second, so that now I can introduce the formula to you. Before I show you the actual formula, we're going to talk about why you can use the binomial and what it really means for something to be a binomial variable. So the first thing that we have to know for a binomial is that the experiment consists of a fixed number n of identical trials. What that means is, for instance, if I was going to be flipping a coin, before I can calculate binomial probabilities, I need to know exactly how many times I'm going to flip. So I need to say at the start, I'm going to flip a coin 6 times. What's the probability I get 2 heads? Or I'm going to flip a coin 10 times. What's the probability I get 4 tails? So at the beginning of the binomial, you need to know how many times you're going to run the experiment. That n, or the number of trials, is fixed from the beginning. The second one is a little tricky. Each trial is independent of the others. It's definitely true when I'm flipping a coin. If I flip a coin and I got 3 heads in a row and then I go to flip again a 4th time, it should be the case that it's still exactly 50-50 that I get heads or tails, regardless of the fact that I just got 3 heads in a row. Where this gets a little tricky is sometimes we model the binomial situation on something like free throw shooting, where we say a basketball player is going to take 10 free throws. What's the probability they make 7 of the free throws? In that case, there is a strong argument that as you're shooting free throws, you get into a certain rhythm, you figure out, all right, I just made the last 2, it's easier to make the next 1. That's a situation where that independence might be challenged a little bit, because really what happened on the previous free throw probably impacts how you're going to take the next free throw. So when we have these binomial situations, sometimes we have to relax that rule a little and just assume independence when it might not actually be true. But the idea of the binomial is that if you know what happened in a previous trial, it in no way impacts what you think is going to happen on the next trial. You still think it's the same chance of success. For the purposes of each trial, there's only 2 possible outcomes. For counting purposes, one outcome is labeled success, the other is labeled failure. So don't get too hung up on the success and failure moniker. It could be that a very bad outcome is labeled a success. If I was running a factory and I wanted to find the probability that a defective unit occurs, I would label that defective unit the success for the purposes of the binomial distribution, but in reality, that unit that's defective is a failure, not a success. So when we say success, it's really the event that we're trying to identify occurs, is what we're saying is a success. Failure is anything else happens. So it has to be a distinct 2 possible outcomes. When I'm taking a free throw, either I make the free throw or I do not make the free throw. When I'm flipping a coin, either I get heads or I get tails. There's no third option. So I couldn't use the binomial distribution to represent a die, for instance. If I roll the dice, I could get a 1, 2, 3, 4, 5, or 6. That would not be a binomial situation because there's 6 outcomes, not 2. But if I take that same die and I label a success as rolling a 3 and a failure as rolling anything except a 3, now I've made it into a binomial situation. There's 2 possible outcomes. One's labeled success, one's labeled failure. For every trial, the probability of getting a success is called P. The probability of getting a failure is then 1 minus P. So if my probability of making my next free throw is 70%, the probability that I miss is 1 minus 0.7 or 0.3 for 30% of the free throws that I miss. For this number 4, we're also saying that we have this set probability of success for every trial. So we know before the binomial experiment begins, the probability that this person makes the free throw is 70%, and that 70% stays static throughout the rest of the questions on that experiment. The binomial random variable x counts the number of successes in n trials. So this is introducing the 3rd variable that comes into play in the formula. We know from the start n how many times we're going to run the experiment or how many trials there will be. We know from the start p what the probability of success is on any given trial. From that p, we can calculate the probability of failure as 1 minus p. We're introducing here in number 5 the 3rd thing that matters. X is the number of successes we're looking for. So a binomial can tell me if somebody is 70% to make a free throw and they're about to take 2 free throws, what's the probability they make exactly one of the 2 free throws? In this example, they're taking 2 free throws, so my n is 2. They make 70% of their free throws, so my p is 0.70 or 70%. They're going to try and make one of the two in order for me to say that's the probability I'm looking for. One success is my X value for this probability, the number of successes that I'm looking for in a set number of trials. One success in two trials. Finally, for a binomial distribution, the mean is given by the formula, the mean equals n times p, and the variance is given by the formula sigma squared equals n times p times 1 minus p. Whenever we have a formula for variance, we can always get to standard deviation just by taking the square root. So if I wanted the standard deviation, it would be the square root of n times p times 1 minus p. As far as where we get the mean formula, this hopefully is somewhat intuitive. If I'm going to flip a coin 10 times and the probability of getting heads is 0.5, 10 times 0.5 gives me 5, or in other words, my average expected value, the mean number of heads that I would get from 10 flips, would be 5 heads. 0.5 times 10 equals 5. This all leads us to this complicated formula. This is the formula that you're going to need to be putting into your calculator in order to get every one of these probabilities. So you're going to be entering this formula a number of times throughout this homework. Expect to have to get used to how to do this. When I put this into my calculator, I know n, I know x, and I know p. Those are the only variables in the formula. This C just stands for that NCR button. So if I know up front, I'm taking 2 free throws, I want to find the probability I make 1, and I'm a 70% free throw shooter. I would put in for n, 2, the number of free throws I'm going to take. I'd then press the NCR button. I'd put in for x, 1, the number of successes that I'm going to try and have. I would recommend putting this in parentheses just to keep everything straight. The next thing I do is put the time symbol, then a new parentheses. Whatever I got is my probability of success. In my example, 70% shooter, so 0.7. To the power of how many successes I want. In this case, 1 success. So this would be 2 NCR1 in parentheses times 0.7 to the power of 1 in parentheses times, when I do this last step, I can calculate 1 minus p or the probability of failure on its own so that I don't have to do it as 1 minus p within the formula, or I could do it as part of the formula. I would put this in as 0.3 instead of 1 minus 0.7. So this is really saying the probability of failure. Parentheses 0.3 to the power of, this n minus x is basically saying if we take a set number of trials and have a set number of successes, the number of trials minus how many successes we have leaves us with the number of failures. So here my n was 2 trials. I wanted to make 1 of the free throws, so 1 success. 2 minus 1 is 1. So this would be 0.3 to the power of 1. The final thing that I'd be putting in would be 2 NCR1 times 0.7 to the power of 1 times 0.3 to the power of 1. So what this formula really represents, this is all the different ways that I could organize that number of trials to have that number of successes. So if I want 1 success in 2 trials, I could go success, failure, or failure, success. What this NCR does is it really calculates how many different ways you could write out that number of successes in that number of trials. I multiply that by the probability of success to the number of successes I want. Then I multiply that by the probability of failure to the number of failures that I want. So that is the full formula that we're using explained. It should feel a little complicated. The best way to get used to understanding it is to apply it and to use the formula. So when I calculate a binomial probability, if I was asked, find the probability we get exactly 4 successes when we have 5 trials and the probability of success is 0.7. I'd set up 5 NCR4, 5 being my n, then the NCR button, 4 being my x, times the probability of success to the power of the number of successes I want, times the probability of failure, or 1 minus the probability of success, to the power of how many failures I want, or the number of trials minus the number of failures. If I put all this into my calculator correctly with the right parentheses, it should tell me the correct probability, or 0.36, 36% of the time. If I do 5 trials with a probability of success of 0.7, I'll get exactly 4 successes. The probability of exactly 4 successes from 5 trials with a probability of success on each trial of 70% is 36%. Again, I recommend you try putting this in. It's easy to get parentheses wrong. It's easy to get some little thing off, which won't give you the right answer. Practice how to put this in your calculator so that you know how to do it when you go to do the homework. Here are 3 other examples to try. If I want to find the probability of exactly 2 successes in 4 trials with probability of success 0.5, I want to plug these numbers into the formula. I'd recommend that you pause the video now, try these 3 on your own, because I'm going to click ahead and show how they would look being put into the formula. So, I apologize, I thought this was going to have it all done out. Since it doesn't, let me talk you through how I would do it out. This problem I would write 4 NCR2 times 0.5 to the power of 2 times 1 minus 0.5 to the power of 4 minus 2. If you put that all in correctly, your calculator should give you a final answer of 0.375. For number 2, I should get 3 NCR 0, 0.25 to the power of 0, 1 minus 0.25 or 0.75 to the power of 3 minus 0 or 3. If I do all that out, I should get the probability 0.422. In each of these, I'm rounding to 3 decimals because I believe that's what Cengage asks you to do for these problems, but make sure that you're following whatever they ask. For the final one, my calculation would be 12 NCR 3 times 0.4 to the power of 3 times 1 minus 0.4 or 0.6 to the power of 12 minus 3 or 9. If I put that in correctly, I should get 0.142 as the overall probability. In each of these cases, what the formula is telling me is the probability I get exactly that number of successes. But there's going to be times where we don't want to calculate the probability of an exact number of successes, but instead we want to calculate the probability of getting less than a certain number or more than a certain number. For instance, assume we have a binomial random variable with 10 trials and probability of success of 0.5. To find the probability that the number of successes is less than 3. Less than 3 would not include the number 3. It would include all possible discrete values up to 3. So if I'm doing 10 trials, I could have 0 successes, 1 success, or 2 successes. And each of those outcomes would be less than 3. Therefore, to find the overall probability that I get an outcome that's less than 3, I need to find, using the formula, the probability to get 0, the probability to get 1, and the probability to get 2. Each time doing the full formula out. If I do that, I can then add each of those probabilities to get the overall probability of getting less than 3. If I was asked to do more than 3, I could run the formula a bunch of times. I could say I'm going to take probability of getting 4 plus probability of getting 5 plus probability of getting 6 plus probability of getting 7 plus probability of getting 8 plus probability of getting 9 plus probability of getting 10. That would give me 7 total times I have to run the formula, each time taking me 2 to 3 minutes, I would say. In the end, that's a 20-minute problem. But if I understand how to use complements, I could say, well, wait, the probability of getting something more than 3, which is 4 through 10, is really everything except the probability of getting 0, 1, 2, or 3. So if you see these questions in terms of the sample space, there's times where it's going to be easier to figure out what's not included as opposed to what is included. If 0, 1, 2, and 3 are what's not included, that's 4 times I'd have to run the formula instead of 7. So there I'd be better off saying, why don't I take 1 or 100% of what can happen and subtract out the probabilities of getting 0, 1, 2, or 3. That way what I'll be left with is the probabilities of getting 4, 5, 6, 7, 8, 9, and 10. If I was asked at least 3, again, I could do the same thing. I could add together the probabilities of getting 3, 4, 5, 6, 7, 8, 9, 10, and do the formula 8 times. Or I could see it as, if I'm trying to get at least 3, that means I'm not getting 0, 1, and 2. So if I find the probabilities of 0, 1, and 2, and subtract them from 100%, that will also give me the probability of getting at least 3. When I look for something like at most 3 means it was either 3 or less than 3, so I would add together the probability of 0, plus 1, plus 2, plus 3. Again, each time running the full formula. If I was asked to calculate the binomial probability that x is less than 2 in 3 trials, I'd have to think what numbers are less than 2, 0 and 1 are less than 2. So I'd have to run the formula for 0, add to that, running the formula for 1. For 0, it would be 3 NCR 0, 0.8 to the power of 0, 1 minus 0.8 to the power of 3 minus 0. Once I get that probability, I would record it in my notes, and I'd run the formula a second time. This time I'd do 3 NCR 1, 0.8 to the power of 1, 1 minus 0.8 to the power of 3 minus 1. I'd get that answer that's the probability for 1. Back in my notes, I have the probability for 0. When I add these two probabilities together, that gives me the overall probability it's less than 2. When I'm asked here, greater than or equal to 4 with 6 trials, the things that are greater than or equal to 4 are 5 and 6. So I'd run the formula for 5, get a probability, run the formula for 6, get a probability, add those two probabilities together, and that would give me the total probability of getting greater than or equal to 4. Here, when I'm asked greater than 2 with an n value of 10, that means I'm really adding up the probability of 3, 4, 5, 6, 7, all the way through 10. I'd be better off if I said, what doesn't this include? This doesn't include the probability of getting 0, 1, or 2. So if I run the formula 3 times, finding the probability for 0, probability for 1, and probability for 2, get that total and subtract it from 1, that'll leave me with the probability of everything else. The final one, the probability that x is less than or equal to 1, well, that includes 1 and 0. So I'd run the formula for 0, run the formula for 1, and add those together. You'll notice that less than or equal to 1 in a discrete random variable is literally the same thing as less than 2. So here's all those probabilities done out. Again, I'm assuming that you know what's going in when I do the formula for p of x equals 4. It's still a complicated calculation, but it's really showing you that if you were putting it into your calculator, 6 NCR 4, 0.5 to the power of 4, 1 minus 0.5 to the power of 6 minus 4, this would give you the probability 0.234. I'd then add that to the probability that x equals 5, and I'd add that to the probability x equals 6 to get this total 0.344. Apologies, I'm realizing I misspoke earlier. Since this says greater than or equal to 4, it would include 4, 5, and 6, not just 5 and 6. If this had instead said x is greater than 4, it would only include 5 and 6. Word problems are probably the trickiest thing to do with these, but it's definitely something that you're going to need to be prepared for. The word problem I've created here is from back when I was driving to campus. The probability that the traffic light is green when Mr. Moulton leaves Manor campus is 35%. Assuming this follows a binomial distribution and Mr. Moulton leaves campus 5 times per week, what's the probability? First, the light is never green when he leaves. If I want to find the probability that the light is never green, that's the probability that I get 0 successes. If I label a success, the light being green when I go to leave. So really here I need to run the formula for the probability of x equals 0. I know that my n is the number of times I'm leaving campus, or 5. I know that my probability of success is the percent of time it's green, If I change this 35% to a decimal, that'd be 0.35. So when I run the formula for 0, it would be 5 NCR 0, 0.35 to the power of 0, 1 minus 0.35, which would give me 0.65, to the power of 5 minus 0, or to the power of 5. When I did that out, I would have the answer to the question, what's the probability that the light is never green when I leave? What's the probability the light is green 1 of the 5 times I leave? Well, if it's green 1 of the 5 times, that's really finding the probability for x equals 1. I'd do out the whole formula for x equals 1 and find that probability. The light is green less than 2 times when he leaves. Well, less than 2 just includes 0 and 1. In parts A and B, I found those probabilities for 0 and 1. If I add them together, that will give me the probability for less than 2. So basically, to get the answer here for number 3, I add what I got in number 1 to what I got in number 2. Number 4 says the light is green at least 2 times when he leaves. At least 2 includes 2, 3, 4, and 5. The only things it doesn't include are 0 and 1, which, good news, we already calculated 0 and 1 in parts 1 and 2. We already added them together in part 3. So if I do 1 or 100% of the possible outcomes, minus the answer I got for 3, that will be the answer to 4. The light is green more than 2 times when he leaves. More than 2 times just changes this ever so slightly. More than 2 now only includes 3, 4, and 5. It no longer includes 2. So to answer this question, I'm going to need to run the probability formula one more time. I'm going to need to run it for the value 2. When I get the probability of it being green exactly 2 times, I can then use that as well as the probabilities for 0 and 1 to combine those 3 and subtract it from 100% to answer this question. Finally, the light is green at most 2 times. At most 2 means 2 or less, 2, 1, or 0. I've already done each of those probabilities out, so I just add them together. The answer I got from 1, the answer I got from 2, and part of this question, number 5, was finding what the answer was for 2. So when I ran it for getting 2 successes, I add that number in. I now know all 3 possibilities, getting a success 0 times, 1 time, or 2 times, and that includes all of at most 2. When I add them together, I'll get the answer. So here is the math for all of that done out. Hopefully you can see this. I know it's a little hard to see because it's small writing. Remember, you can always click on the actual PowerPoint that's uploaded to Canvas if you want to be able to see this more clearly. But basically written out, the probability of x equals 0 is 5 NCR 0 times 0.35 to the 0 times 0.65 to the 5th. For that, I get 0.116. When I do the same math for 1 success, I get 0.312. That means less than 2 times are these 2 added together. 0.116 plus 0.312 gives me 0.428. When I want to find at least 2 times, that's x being greater than or equal to 2. So all I do is I subtract from 1 the probability of 0, 0.116, and the probability of 1, 0.312. Really what I end up doing is taking 100% minus this answer I got for less than 2, 0.428. That gives me 1 minus 0.428 is 0.572. For number 5, I first have to run the formula for 2 successes. When I do that, 5 NCR 2, 0.35 to the power of 2, 0.65 to the power of 3, gives me 0.336. If I then add that together with 0 and 1, that gives me 0.764 as the probability that the light is green at most 2 times, meaning 0, 1, or 2. If I then want to find more than 2 times, I subtract 1 minus this 0.764 to find it's 0.236, that it's green more than 2 times when I leave in a given week, that I leave 5 times.